that. And it's about enigma and given clause guidance. I will tell you what enigma is and you will see. So, in the first section, I will give you some basic introduction to ATPs and what are given clauses. Then I will tell you about enigma models. And in the last section, last two sections, I will summarize the progress that we did basically in the last year. Okay, so let's start. So, we are working with automated theorem provers, and automated theorem provers in first order logic usually represent their program as a set of first order clauses. First order clauses are just clauses, just a disjunction of literals, and literals is either an atomic formula or its negation. Everything is prepared for a proof by contradiction. So when you want to prove from some axioms, you want to prove some conjecture, you take the axioms and you negate the conjecture, you translate everything to the clauses, and from this initial set of clauses, you are trying to infer an empty clause which stands for a contradiction, for example, using resolution-based methods and so on. So, resolution-based theorem provers basically have some loop which looks like that inside, and usually they divide the clauses into two sets of processed and unprocessed clauses. At the beginning, processed clauses are empty, unprocessed set of unprocessed clauses contains all the clauses at the beginning. Then there is a loop which says, while we have no proof, then select some clause from unprocessed, apply on inferences. Well, this clause is called a given clause. So we select one unprocessed clause, we call it a given clause. We apply all inferences rule of the given clause and all the previously processed clause, and we move a given clause to the set of processed clauses, and we put the newly inferred clauses to the set of unprocessed clauses, and we iterate and we go on unless we reach an empty clause, or we cannot go on anymore. So, we will work basically with this e-prover, and okay, the main point of this loop, the crucial point, is the selection of a given clause. When we know how to select the right given clause, then we can directly basically find the proof, but it is quite difficult to know which clause should be selected as the next. Okay, so that's why every prover solves this in a different way. And for example, in e-prover, there are several predefined clause weight functions, and other clause weight functions can be easily implemented. Each clause weight function simply assigns a real number to the clause, and then the e-prover simply selects the clause with the smallest weight, so it takes the lightest clause. So just remember that the smaller weight, the better. So the smaller clauses are processed at first. Okay. E-prover, we will work with we will talk about e-prover strategy. So by e-prover strategy, we mean the set of all e-prover parameters that somehow influence proof search. It might be term ordering, literal selection function, clause splitting, premise selection, and their arguments. Important part of e-prover strategy is the clause selection function themselves, and e-prover allows, implements, or provides a simple domain-specific language which looks like this. In this way, we can combine more than one weight functions. And for example, there is some clause weight function 1, 2, 3, and we assign to each of them a frequency. The frequency says how often this clause weight function should be used to select a given clause. For example, in this case, the first clause weight function will be used 10 times more often than the second one. The third one will be used 20 times more often than the second one, and 2 times more often than the first one. So this is very simple. Now I will tell you more about enigma model. The basic idea behind enigma is that we want to use some fast linear classifier to guide given clause selection. fast is important because eProver can process several hundreds, even thousands given clauses per second, and we don't want to slow it down too much by our guidance. So Enigma is an acronym and it stands for Efficient Learning-Based Inference Guiding Machine. So you can see that it's, by itself it's a little bit enigmatic. For example, you can see that there is N, but it could be also this N or this N. Yeah, we never know, so we choose the middle N. So this is Enigma. And the important thing is that we use linear classifiers. Linear classifiers are sort of stupid, but they are very fast. And that's what we rely on. We sort of trade precision for speed. So we use very simple classifiers, but they are very fast, so we will be able to process a lot of clauses. And even if we select sometimes some bad clause, it won't really affect us because we will still be very fast. Okay, so what we use is a linear classifier, which is an open source library. We use an open source library linear, can be freely downloaded from internet. And how linear works, it is a classifier on float vectors. So as an input to linear, we give it two sets of float vectors, positive and negative examples. Now, then you run the linear training method. It uses some linear logistic regression method, so it outputs a model. All the positive and negative examples has to be represented as float vectors of a fixed dimension. So all the vectors have the same length, and the output of the training is again another vector of weight, which is called a model, and the model has again the same size as the training examples. And then when you want to evaluate an arbitrary vector, a generic vector, you just compute a dot product with your vector with the model vector, and when the dot product is less or equal than 0, then you classify it as negative. When it's greater than 0, then you classify it as positive vector. So it's very fast because dot product of two vectors can be computed in the time linear to the dimensions of the vector. Linear work is vectors, but we want to classify clauses. Okay, we want to help eProver to recognize which clauses are useful and which are useless. So we need to somehow represent clauses as feature vectors, and to do that we do a very simple transformation with a clause. So we can take a literal, we can write it down as a tree, which looks like this, for example, and then we unify all the variables, so we translate all the variables, we replace all the variables by some special symbol. We do this also with the Skolem symbols. We unify all the Skolem symbols with some special, we rename all the Skolem symbols with some special symbols. And additionally, we add one root node to the node, which says whether it is either plus or minus. It depends whether it is a positive or negative literal. In this case, this is a positive equality literal, so we give plus in the root. If it were negative equality, we would put minus. Okay, so this is very simple. Then we look at this tree, and we count all the descending paths of length 3, which are just triples of symbols like this, equal f star or equal g dot, and so on. So those will be our features, triples of symbols. So when we have some training examples, we collect and enumerate all of the features. So we put them in a table and we assign to each feature a number. Then we simply count the features. So for example, here we have a feature which says plus equals f. This corresponds to these 3 symbols, and we see that this appears in this literal, it appears just once, so we put 1 here. Here we have, for example, 2, it says that we have a feature equals f star, and we see that equals f star appears 2 times in this tree, so we put 2 here. This first 2 columns are fixed for all the clauses, and only this column contains all the features which appear in the training examples.
Question? Why only 3? Parser plate 3? This is.
Yeah, okay. Well, I will talk about it a little bit more, but the thing is that 3 gives you more information, more precise classification than 2. Yeah? And if you take 4, then you will have too many features, so you can get lost in it. So sometimes we have decided that 3 is the right number, and
you can hash them.
Sorry?
You can hash them.
Well, yeah, we basically do something like that.
Okay.
So then we simply take the third column. This is the vectors of counts, and this is our feature vector. So this is how we translate a literal to a vector. And when we want to translate a clause to a vector, then we simply translate literals one by one, and we simply solve the vectors. Okay, so that's how we can translate a clause to a feature vector. Then, so how we construct an enigma model. So we basically, at first we collect some training examples. Training examples can be obtained from eProver runs. eProver has an option which is called training examples, and when you run eProver with this option, when it finds a proof, then in the end it tells you, okay, I have processed all of these clauses, and so all of these clauses, this much was really useful, it was necessary to process them, and the rest of them were not really useful. We could they were not necessary to be processed. Okay, so we could have missed that. So then we enumerate all the features. It gives us simply some function which gives us for each feature an integer, which is the index in the feature vector where the count of these features will be stored. We translate all the clauses to the feature vectors, and we train a linear classifier. Linear classifier will output again a vector, which is a float vector, which has the domain, which is the size, the length of the number of features. So for each feature, we have one position in the vector. And this path, this is this n feature enumeration, and this vector is what we call enigma model. Once we have an enigma model, we can use it inside eProver to guide given clause selection like this. So suppose we have some enigma model E, and we want to evaluate some generated clause. Suppose we have just generated some clause C, and we want to tell eProver this is either a good clause or bad clause. When it is a good clause, eProver should process it as soon as possible. So we compute a prediction. So at first we translate C to feature vector using this enumeration of features, and then we simply compute the dot product with the model vector. When the dot product is greater than 0, then we set the weight to 1. Just recall that I have said that the smaller weight the better, so eProver will process the clauses with the smaller, the lightest clauses will be processed first. So 1 means that this clause is classified as positive, 10 means that this is classified as negative. At the beginning, we were using just this weight function inside eProver, but what was happening that it didn't work much. Okay, so what was happening that the eProver somehow gets stuck, and it kept processing longer and longer clauses, and all of them were classified as positive, but it was not good for us. Okay, so we have decided that we need to force eProver somehow to prefer smaller clauses. So we have just included, we have combined the prediction weight with the length of the clause. So this is the length of the clause measured in number of symbols, and this is some multiplier. Okay, so this is a multiplier. We take this number and we add length of the clause multiplied by some multiplier delta. So what now happens is that when when we have some really long clause, even when it is classified as positive, then it will have a bigger weight than some negative clause, than some short negative clause, okay, because we will have something 1 plus something relatively big, or we will have 10 plus some small number, so it will process negatively classified short clauses before and before long clauses. Well, it happened because I said that we are using simple linear classifier, and so sometimes it does mistakes, so sometimes it misclassifies a clause. So that's why this was necessary. Okay. Now, inside improver we have implemented enigma weight function, which simply implements the previous equation from the previous slide. And now when we have some improver strategy, just recall that the improver strategy contains a weight selection pattern like this. Okay, it is a combination of several weight functions together with some frequencies. And when we have some improver strategy, we can plug in enigma models to it into two ways. Either we completely ignore all the weight functions that were previously present in the e-heuristic, and we just allow we instruct improver to select all the given clauses by enigma classifier. Or we can use enigma with combination with the original weight functions, and we put so we insert enigma classifier with the frequency, which is the sum of the frequencies of other weight functions. So in this way, half of the clauses roughly will be selected by enigma, and half of the clauses will be selected by the original clause selection mechanism. Okay. Just from this slide, just remember that there are two ways how we can combine enigma models, how we can plug in enigma into an existing improver strategy. Either we use enigma alone, or we use enigma weight functions in combinations with the original clause weight selection mechanism when we have some. Okay, so then we have now I will describe basically the work that we have done in the previous. Well, this enigma models we have implemented this basically it was already done a year ago. So this is just the work that has been done in the last year. Okay, so we have sort of enhanced new features. So you can have mentioned that enigma classifiers are independent on the goal conjecture. So when we have some goal classifier, we have some enigma models, an enigma classifier, it keeps recommending the same clauses independently on the conjecture that we are currently proving. This does not sound really right, because when we are proving one conjecture, some clauses should be recommended. When we are proving different conjecture, it makes sense to recommend different clauses. Okay, so that's why we have extended the features vector with conjecture features. So instead of feature vector for the clause, we take a feature vector which is a vector of the twist in the size. So it has the length. It has a double length than this. So it is just the double vector, and it contains, in the first part, it contains the conjecture features of the clause, the features of the clause, and in the second part, it contains the features of the clause of the conjecture that we are currently proving. Then, in the training examples, this conjecture corresponds to the conjecture which was being proved when this training example was generated. So we know from the training examples, we know that this clause is positive when we are proving this conjecture and so on. Then we did some experiments. We did some evaluation how the conjecture features help with prediction. Okay, so we did on two independent benchmarks. So we use aim benchmarks and some Nizar benchmarks. Aims are algebraic problems. Nizar are translations from Nizar library. Here we say here you see training accuracy without conjecture features and with conjecture features. Here you see that on the AIM project it didn't really help much, but on the Nizar it helped a bit. This line 50-50, this corresponds to boosting. Basically what happens when we run improver, we have much more negative examples than positive examples. Usually this is the ratio, this is something like 90% of the examples are negative and only 10% of them is positive. Well, when you do this, then in this setting you can take a trivial classifier which classifies everything as simply as negative, and you will obtain 90% accuracy with this trivial classifier. So that's why we do sort of boosting. We repeat the positive examples so many times so that the number of positive and negative examples is the same. And we did the tenfold cross-validation. You can see that the numbers don't really differ much, which is good for us because it means that our classifiers are not really overfitting. So one note about this AIM. In the AIM project, all the conjectures basically they are very similar, they look alike. So when we add the conjecture features, it didn't help much because all the conjectures are sort of very similar. So that's our explanation why conjecture features help more with Nizar than with AIM. Then we added also horizontal features. So whenever we have some function application, we create a feature which, when some function f is applied to some symbols, then we say we take the top level symbols from the arguments and we create a horizontal feature. So for example, here you can see that we have some function f applied to two variables. Here we have some colon symbol applied to variable, and so on. We just take the top level features. Then we also added some static features like cross, like number of positive and negative literals. Then we also count the number of positive occurrences for each symbol and number of negative occurrences for each symbol. We also count maximum depth of each symbol. For example, this says that there is the maximum depth in positive letters for symbol which corresponds to variables is number 4, and really we see 1, 2, 3, 4. So this is really very this is the maximum depth. Now we did some experiments with boosting and looping. So training data, I have already said that they are uneven. Usually we have more negative examples, usually roughly 10 times. So our previous attempt was simply to repeat the positive examples 10 times. You know, it worked a bit, but then we decided, okay, can we do something better? And we came up with this following algorithm. So we collect the training data, we create a classifier, and we use again this classifier to compute the predictions on the training data. The training data already contain predictions, so we know the right answer, and we know the answer given by the classifier, so we can see which clauses are classified correctly and which are misclassified. We compute prediction accuracy differently on positive and negative examples, and as long as we have the accuracy on the positive examples is smaller or equal to the accuracy on the negative examples, then we simply repeat misclassified positive clauses in the positive data. It is better for us when we misclassify a negative example as positive, because then we just process one more clause. It's not a big deal. But when there is some positive clause which is really useful and we misclassify this as negative, then it can really affect the proof set, because it might be a clause which is necessary to be processed and we postpone this processing, or we never process it at all and we might never get to the proof. And we simply repeat this unless this condition is fulfilled. Then we did also some looping experiments. So for example, when we have some strategy S, and a set of benchmark programs P. We evaluate strategy, improver strategy S on the programs P, on all of the programs P. We collect the training data, we create classifier from the training data, and now just recall that I have told you that there are two ways how to extend improver strategy with Enigma model. Either we use Enigma model alone to select clauses, or we use it in combination with those clause selection functions which appear in S. That's why we obtain two more new improver strategies. We evaluate them again on the programs, we obtain more training data, and we repeat this algorithm. One thing about this algorithm is that it does not end, does not terminate. Yes, so the question is how many times should we repeat this loop? So far we do it 3 times. Don't ask me why we just do it 3 times. Okay, so then we did a simple experiments with clustering. So we do MPTP benchmarks, which are 2079 or 78 programs coming from wizard translations, and we have selected 10 improver strategies from improver automode. Programs in the MPTP benchmarks are naturally clustered into 33 categories, which are for articles, and we train Enigma model separately on each article for each of the 10 strategies. So we will have 330 Enigma models. Then we also do the boosting and looping, and we combine it. So instead of one model, we end up with 10 models. So in the end we have 3,300 Enigma strategies. 3,300 strategies. That's quite a lot. So we simply take the best performing strategies on each article. So then these are some selected results from the selected articles. So you see the number of programs in each article. This is what is the best performance out of the 10 improver native strategies, and this is the best Enigma strategy. You can see that sometimes we don't get much more, but we are never more. So this is sort of good. But sometimes you can see that we can have 60-70% improvement, which is quite nice. Okay, so we have evaluated these our Enigma strategies on these articles with some low time limits, something like 5 seconds, and then we selected 62 best performing Enigma strategies, and we did a sort of fair comparison with E in auto schedule mode. So this is the results, or those are the results on the all programs of the MPTP library, on those all 2078 programs, and the time limit for each program was in this case 300 seconds. So in this case we can see that E in auto schedule mode was able to solve 1,343 programs. Those 10 strategies that we have selected from the auto schedule mode was able to solve 1,397, even though auto schedule mode contains all of these 10 strategies and even more. But we have been sort of cheating, because we have evaluated all the strategies that were in the auto schedule mode, and we took only those 10 best ones. So, but in the end, our Enigma strategies, 62 protocols. Just by the way, a time limit for one program was 300 seconds. So it means that, for example, in this case, when we have 10 strategies, the time limit was evenly divided by the 10 strategies. So it was each strategy was run for 30 seconds. In this case, it was 300 divided by 62. So Enigma strategies were able to solve 1,450. Here you can see what are the number of programs which are solved by this portfolio, but not by the programs which are additionally solved by this portfolio to the autos. So those are the problems. This portfolio solved 25 more problems than auto, but it was 79 problems. Now Enigma models were able to solve more than 100 problems, but it was 50 problems. Of course, we can combine these autos with Enigmas, and we will get something like almost 1,500 problems or something like that. Okay, so that's basically all. And this is a picture from yesterday. This is for those who were not able to get above the sky. So thank you.
Do you have some statistics how much each of these extended features has improved the performance?
Yeah, okay. When we did this experiment, without the conjecture features, without horizontal features, without static features, and all the other stuff, we were getting worse result than others. So when we implemented all of this, it helped, but I cannot really tell you right now what was the improvement, what was, what helped the most and so on, because we will need to do separate experiments, with one feature, then with the second, and so on, and it takes time. We will do it probably, but we don't have it right now.
So what time do you spend in? So what is the overhead of doing this linear?
In the learning?
So let's say how much does it reduce the number of steps in the same time if you do that? Is it negligible or?
The number of process clauses, for example? Yeah, well, I did some measurements, and in average it reduces the number of process clauses 3 times, basically. Okay. So, but it's an average. Sometimes it keeps it the same, and sometimes it reduces it, for example, 10 times or 15 times. Sometimes it really helps. When you have the proof, sometimes it's, for example, directly follows the proof. So instead of, for example, 1,000 process clauses, you have suddenly something like 20. You just need to turn off improver's option to prefer initial clauses, because then it keeps processing initial clauses and ignores your recommendations. So it's just
Any more questions? Okay, well, thanks again.
okay. We need to put this. You want microphone?
Right, I'm going to point out for a start that the alarm clock is nothing to do with me, it's not that cruel. Okay, so I'm reliably informed that I probably taught this guy machine learning when he was undergraduate, and this is therefore the first time I've ever introduced an ex-student at a conference, and now I feel really, really old. It's easier ex-student, this better be good. So, my next product.
Hi everyone, I'm Michael. I work at Manchester. Not too long ago, Sean taught me machine learning, so I'm now sweating a little bit about my statistics. So I work with Vampire as their improver. So this project in general, I'd like to make 2 things clear. First of all, I made up the name entirely. If someone has prior art on this, I'd be willing to change it. Secondly, it's very early work, so if any of the choices are made along the way seem dubious, misguided, that's because they are. Tell me about them. So I'll just give a bit some background on theorem proving, and so on. I know most of you here work in theory proving, so maybe not great, but I'll just briefly skim through. So as computer scientists, as linguists, as mathematicians, even engineers, often what you want is you have a proposition and you want a proof of that. We want to automate that. So we want to have a prover that does some sorcery and translates a proposition into a proof. So it's been a while, we've worked on automated theorem provers for some time, so we've got some folklore about it. The first thing everyone agrees on is it's really hard. It's not an easy thing to do. Whatever logic you do, it's not easy. So to deal with that, you need multiple heuristics. Some of them complement each other, some don't. And you need some very, very careful engineering to make sure you don't blow up the search space, you don't want to take too much time. And any algorithm you might choose either solves your problem quickly or it doesn't solve it at all in most cases. The problem is quite ill-conditioned. If you make small changes to your prover, it might make a huge difference on certain cases and so on and so forth. And generally in automated theorem provers, performance matters. If you can squeeze out a few more cycles from your theorem prover, that might be the difference between a proof and not a proof. However, so far, the theorem proving community has generally cared more about whether or not you find a proof within a time limit versus the average time in which it takes you to find the proof. In the case where you use this as a hammer, for instance, in interactive theorem proving, you might care more about how long it takes to get back to you on average rather than whether or not it finds every proof for you. I want to change this a bit. So I use Vampire. Factually, it's an automated theorem prover for first order logic with equality, and I use it as the experimental testbed for this project. And I'm obliged to use some advertising, so it's a very high performance prover. It does well in the theorem proving competition CASC. I'm sure you all know Andre, and he's very keen for you to go and use Vampire. It has a new license, which is less restrictive than it was previously, and a new website, so you can go have a look maybe. I'm reliably informed that it will be shortly shipped with Isabel, the interactive theorem prover, which is an improvement. So how does Vampire work? The main algorithm it uses is a resolution-based loop. So the important thing here is that it's an iterative process. You might think of theorem proving as a true search, and that is the case sometimes, but the main algorithm we use is iterative. You start with a set of clauses, and you resolve those clauses to produce other clauses, and hopefully at some point you produce the empty clause, and at that point you're done. So you churn along looking for a proof, and eventually you find it. So how do we guide this? Well, we have different heuristics, and we have different parameters we can tune. We've got knobs on the side of Vampire. We can just turn a little and change the behavior slightly. So we call these things strategies. In Vampire, they consist of an algorithm. So whatever that might be. So for instance here, this is the discount loop. So the red bar. Some parameters to that algorithm. So we have a load of different flags we can tune. So some parameters. And how long it takes to run, so how long we're giving the strategy to run. So we run several short strategies rather than one long strategy. This works better in general because, as I said earlier, usually you either find the proof quickly or not at all. So it's better to run multiple other algorithms rather than one singular long algorithm. So you want to find schedules of strategies, that is, lists of strategies to run in order. So you might think, solve a problem, right? So yes, they're good, much better than using one strategy. They have a minimal overhead compared to other methods of equivalent things at runtime. And they're an engineering opportunity. They allow you to explore the space of design more than you would if you had a singular strategy. So that's good. We also run them in parallel in Vampire. So we get very cheap parallelism. We spawn a new process for every strategy, up to a pool of however many cores you have. So we run one process per core, and that's how we do parallelism in Vampire. Not so great, however. There's a few problems. So it's very difficult to find what you might call the best strategy schedule for whatever that might mean. It also means that the scheduling file that we have is unreasonably large. It contains a lot of data, and it's manual, tedious work to update it. It doesn't really work very well. We'd like to get rid of it. The engineering you produce with strategy scheduling is also quite brittle. If you change one thing, it might not work so well. There's been multiple instances where changing a single parameter means we haven't found a proof for something. And the main problem which I'm trying to address is that if your succeeding strategy is somewhere late in your schedule, that might mean that you don't find it until later. So in the ITP case, that might mean that you're waiting 30 seconds, a minute, 2 minutes, when you should have been waiting 2-3 seconds. So there's a couple of easy fixes you might do. That's a quick fix. So we've tried round robin scheduling. So spawn processes for every strategy and then run them in time slices. So we turn this sequential schedule into a looping schedule. You take very small slices. So if, say, strategy number 4 succeeds, then, okay, so we run the strategy of 4 the first time, doesn't quite get there in time. Next time around, maybe it gets there. That might be better. It doesn't fix some of the issues, it's still quite brittle. And it introduces context switching overhead. Depending on how long the slices are, that can be significant. And you also get some memory pressure. If you have to spawn every process that you have in the strategy schedule, that could be a lot. And it doesn't seem particularly smart. It seems like we can do better. So, okay, so you've got a list of strategy schedules and you want to decide what goes first. Okay, maybe we can do it before we start running. Look at the input problem, guess what it might be. Okay, we think this strategy works okay on this one. Fine, let's do that. So we do some version of this. For instance, if the problem contains arithmetic in our problem, so, oh look, we found a plus sign, must be arithmetic, then maybe we know that some strategies work better on problems with arithmetic. That's good in that we don't have any runtime overhead for this. When we're running, after we've decided our strategy schedule, there isn't any overhead. It does feel a little ambitious, however. You don't necessarily know what's going to work well, it seems hard, it's not obvious. And if we can't do it, why can we expect our machines to do it? My proposal is that we do so-called dynamic strategy priority. So if the previous one was static, this is dynamic. So run a standard schedule, but every so often stop and check the running strategies. See how they're doing, checking on them. And we want to look for strategies which look like they're succeeding or failing, and we want to prioritize the ones that look good and deprioritize the ones that don't look too good. So here we turn our example round robin strategy schedule into one where, oh, number 4 looks promising, let's extend it a bit, and then we find the proof. Done, sorted. So there's a question here, how do you look for strategies which look like they're going to do well? But we don't, we have no idea. So we want to find something, some function of running strategies that makes it look like they're going to succeed or fail. We've got no idea what. We didn't know what to look for.
It's the next talk.
Okay. Even better. So I don't know what to look for. And there's a large space to explore. So in Vampire we have a lot of different features to look at. I found, while digging about, 400 odd features, which contains some properties of the proof search, some statistics about how we're doing, and the option values we passed in. So just looking at numerate values, I found 400 odd. I'm sure there's probably more you can do. This excludes computed features. So if you wanted to compute some function of other features, I don't look at that so far. Maybe I should. So what I do is I report every feature. I want to be agnostic about this, I don't want to do feature selection, so I don't know what I'm looking for. So I report every feature, and report a feature vector every k steps around the loop. So I get a decently large set of execution traces, by which I mean lists of these feature vector reports, which I get from running Vampire on the set of TV programs. And then I tag these traces whether they succeeded or whether they failed. So this is what one looks like. Again, not obvious. And it doesn't matter what's what. I haven't even looked at what these lines mean. These are just the values over time. So the lower axis is the number of steps so far, and the y-axis is just the values taken. So got something. It looks a bit like this. It's not ideal. For a start, we have integer values. We want real values. That's not so hard. But we also want them to be preferably zero mean and unit variance. We want them to be machine learnable. We want them to be a fixed size as well, ideally, and preferably in a sort of square grid-like fashion, because what works best for the current tooling we have in machine learning. Preferably, we don't want them to be too voluminous. What I got was multiple gigabytes of this stuff, and it took a while. Another problem we have is that by definition, we have more succeeding traces than failing traces, a lot of them. So, came up with some ways around this. I'd be very pleased to hear any better solutions to what I came up with. So, far more failing than successful traces. Now, I in the previous talk did some boosting. I chose to do the opposite. I just chose a subset of the failure traces. Maybe one is better, I don't know, I'll have to find out. The traces are of differing sizes. I want them to be roughly grid-like, and they're of wildly differing sizes. Sometimes it's no data at all, sometimes it's multiple megabytes of data. Depending on how long they ran for. So what I did was I changed it to be a fixed length by bucket averaging. So what I mean by that is I chop it up into sections of a fixed number. I chose 10, but pick a number, any number, so that you get the shape of the data rather than the actual data. Debatable. We also want to run get these predictions based on the strategies as they're running halfway through, not as they're finished. We only have finished strategies. So I chopped them up a bit. I took the first quarter, first half, the first 3 quarters, and the totality. That seems to work okay. I'm sure there's a better way of doing that. So there's an actual solution here. The traces contain very high variance, very large ranging data. You do feature scaling. You just map them down to a smaller range. That's actually a solution, I think. So this is what the previous trace looks like after you post-process it. So the bands represent features I look at, and time is now vertical. And that looks a bit more promising. Color is the value. So how do we classify this? Now, I know certain people are more inclined towards a Bayesian method or a classical method. I chose to use a neural network just because it was there. I'm sure other classifier technologies will work fine as well. So I used a vanilla single hidden layer neural network, a convolutional neural network, and a gated recurrent unit, which is a recurring neural network used for sequence classification usually. So if anyone's interested, I use the Keras library to the wrapper for TensorFlow and other things. So this is the results I got from this data set. It's around 10,000 data points. So this is quite surprising for me. For a start, it's bizarrely high accuracy. I did not expect this. I was expecting to get around halfway, if that. It didn't seem like it would be an easy problem. There's also surprisingly little difference between some of the methods. So if we go back a slide, I would expect something more complex, like a recurrent network, to more significantly outperform a simple neural network. But
So I have a question. So accuracy, what does it mean? So what? So how many classes or how many? So what do you mean by accuracy?
Right. I just classify whether they're going to succeed or fail. So a binary classification. Does that answer your question?
Okay, and you evaluate it on a data that is 50-50 failing and succeeding?
Yeah, exactly. So I've removed
Okay.
all the failing traces that I didn't want, so I just took a random sample of failing traces so that I get a balanced data set. So despite expectations, a simple neural net suffices. And it's much simpler, much more performance than other classifiers. Overhead is a problem here. We want to be as quick as we can. It's also quite easy to implement, so that's good for me. So implementation turned out to be the hardest part of this project. I thought that perhaps the machine learning would be harder. Turns out that actually doing the engineering is non-trivial. So it's obviously challenging if you have a more sophisticated classifier in your group. For me, not so bad. It's just a simple loop around, multiply some numbers. What we did was we trained the network in a Python context and then generated some C code, and that seemed to work okay. It's also nice that there's no dependencies solely attached to your program. So what we want to do is spawn all the strategy processes simultaneously, and then decide which ones are going to work better and run this first. Unfortunately, that means that one, you get memory pressure. On a reasonable desktop machine, we ran out of memory. On the Star Exec machines, not so much, but if you want to run it on a reasonable machine, then yes, it's a problem. It also takes longer to spawn up a lot of processes. That is not so good for the common case where you find a proof quickly. Vampire is a reasonable ATP. It finds things quickly frequently. So we don't want to suddenly penalize everyone by 5 seconds. So if we can't have all the strategies running at the same time, what's the point? We can't. We still have to do it sequentially. So there's a compromise here. We keep a pool of running processes, and we do it partially sequentially. So we still run through them sequentially and put them in the pool. But we check the pool frequently, and if anything's falling below a static threshold, then we move them out of the pool. So it's still possible to have all the strategies running simultaneously if the strategies run in reverse order, if that makes sense. However, it's unlikely, and you get most of the advantages that we want without having to run everything simultaneously. So that's probably not clear. So here's a simplified diagram of what works. So we have this queue. Initially, this is the strategy schedule. When we need to move something into the running pool, we just wake one of these up. We run it for a time slice. If it manages to find something, then good, proved, stop the world, we're done. If it gives up, again, so what, drop it. Or its time slice will end, in which case we run it past the predictor, and the predictor goes, okay, I think it's this likely. We move it back into the queue with that predicted priority. So we ran some benchmarks. Thank you to the runners of Star Exec and the TPTP problem sets. We wouldn't be able to do what we have without them. So we compared it to the most recent Vampire release without any modifications. TPTP has around 20,000 problems on what we wanted. So turns out my modified version isn't very good at solving more theorems than the baseline Vampire. Both provers solved around 12,000 of the 20,000 problems. Okay, so not disastrous performance. But my prover proved 100 more proofs than baseline Vampire, distinct proofs that Vampire didn't solve. But Vampire proved 600 proofs that I didn't solve. Not so great. However, on the benchmark for speed, I did much better. So moved it from 10.5 seconds per proof on the whole data set to 8.5 seconds per proof. Maybe that's something you care about if you're doing an STP. I also compared it to the round robin scheduling you saw before. I'm better than that in both aspects. So good, we can improve on that. So to wrap up, it's very early work. Most of the decisions I made, I don't think are particularly good decisions. But the classifier performance is pleasantly surprising. I think that's probably quite good performance. Maybe we can do something better with that. I'd be interested to hear what you think about how I implemented this in a proven. I think there's probably a large design space to think about here that we can do better with. And it's maybe an unfair comparison to draw against the baseline vampire. So vampire already knows which strategies are likely to run better. So we've already crunched the numbers on this. Vampire already has some idea of where strategies are going to go. That's why we have static code. So maybe it'd be more fair to do a randomized schedule and see if that plays better. So, yes, any feedback or ideas would be welcome, and any questions?
I don't know how automatic Andrei's magic box now works, but it would be useful to have a separate training and test set.
Exactly.
So maybe take 15,000 TPP to just build a vampire and your system and compare them on the other 5,000 to eliminate the aspect that vampire has essentially memorized TPP like he has to.
Yeah, so that's very much the case. I need to work out how Android's magic box actually works. It's very magic.
Yeah, I had a completely similar point. I would even forget about TPTP because Andrei has been tuning on TPTP for the last 20 years. So take something like Isabel, Mizar, KKML, whole programs,
Okay.
which are actually your users. It seems to you are going to sell this to the Hammer users, and do whatever Andrei is doing on like some training set, and then evaluate on some testing set and compare it with what you are doing.
I guess you could do some profiling, like to find out how much time your original apparatus that you created, how much time is that taking? How much time are you stealing from vampire?
About 10%.
Sorry?
About 10% of total.
Is that
all time?
Okay, right. Okay, so that's really good.
It is not bad.
Is there no room to improve?
I'm sure there is, yeah.
No, but it's really, I mean, I assumed it would be like half or even worse. You know, there
Yeah.
seems to be a lot of engineering there for you to take cycles away from vampire and do what it does best. So it's impressive. It's, I know people who've optimized things and they work 10 times slower.
Yeah.
So, it's a very good process.
Have you measured what features are the most distinguishing ones?
I should do that, yes.
Okay.
Unfortunately, with neural networks as opposed to more sophisticated models, you can't really just read off what the features are doing.
So is it a single layer neural network?
It's got a single hidden layer.
Yeah, then it's not so hard.
So I need to go through and crunch the numbers about what makes the most difference. Yes, in principle, yeah. Yes, to answer your point about why it's so speedy, I think it's because the neural network I use is so simple. It's just two compiled multiplication loops. So looking at the assembly produces this reasonably efficient. It does its job.
But the wiring that you've done, personally, the engineering you've done doesn't seem to be slowing things down, which is really good.
Great.
Okay. Any more questions? Okay, thanks again. I think we're breaking now for coffee, so we'll come back at 2:45 for the last session.
I'm not sure there is a coffee. The coffee was before the session, so,
Okay, so it's
you can pay probably for the coffee.
When do we start this?
For
Already
This is surprising. I wouldn't expect it.
Das sind die in Zeitungsartikeln evaluiert wurden. Also nach der Normalisierung, bevor sie in Anschluss geschickt werden. Das ist die Stärke davon, dass die noch evaluiert wurden, die ist ja die. Das heißt, ich aktiviere mich an der Stelle, das wäre der nächste Team. Weil ich auch nicht das gleich. Und das ist Shared Service, kostet das nicht zu behalten. Also die Pause selber ist klein, sind fast sehr intensiv bei der Rechnungsform angefangen. Und zu lesen, also man hat jetzt die gesagt hatte, ja, ich habe dann eine Liste aller Klauseln, die, das ist eine Zollreferenz, ja, die Jubiläumsklausel wird zitiert von der Prozedur verarbeitet wurde. Normalisiert kann ich vielleicht, und ich weiß noch genau, welche Version von der die gebe ich dann aus, wenn sie im Beweis vorkommt, also der Zoll vorkommt, und dann positiv und nicht dann negativ. Ja. Und der Seiteneffekt ist auch eine Chance, dass da kalkuliert werden. Das sind nur relativ viele, weil ich weiß ja auch, dass das jetzt weniger arbeitet, ja, das ist Arbeit, müssen arbeiten müssen. Ich werde jetzt auch als ich habe es halt das Code ausschreiben. Das interessiert aber nicht. Wenn ich das Schuma habe, lasse ich nicht mehr da. Du kannst viele andere Optimierungen machen. Ich werde dann ausgeführt, dass die Seite nicht mehr ist, weil ich nur mal intern recorden. Ich würde vieles einfacher.
Yes, they're my first floor. So basically,
Can you find it for me?
Not shared.
Can you make the conjecture of the
Can you
Okay.
you can also
Predict null sec, and it could be predict null sec
okay.
new rather than
Okay,
predict
I'll try those.
No worries.
You could also just make the conjecture the oldest, the newest stuff.
Well, we want to do it quickly on something like 100,000 examples.
Yeah, that's change. You don't want to re-export every time.
Yeah, we don't want to load it 100,000 times. Like
Okay.
Too much time.
Okay. You just remove one and you predict, and you remove one and predict for it.
Yeah, well, in all these cases you are describing, we would have to hack Cesare's thing. I'm willing to hack my Perl thing,
Yeah.
but I'm not willing to hack Cesare's thing. I think,
Yes, rewrite it.
I think this is the C++.
Yes.
Yeah.
I think someone should rewrite the C++ to C++.
I think Cesare did basically the thing which I now showed to Lasse is the
The nosec, and then is in the make file or something, and it doesn't produce this binary by default.
Yeah. Didn't he call it cock mode at some point? There was something called cock mode, which Cesare explained to me was actually no sequence, but I'm not sure whether it was the no sequence thing. Oh, please let water too.
And you also need know that when you say no sequence, you say also know that it includes.
Well, we don't insist on that, but we don't have any dependencies for this particular application. So it's really just we really just want the nearest neighbor.
You could have dependency without sequence, I guess. But if you you can do a cycle. It's somehow you depend on. There's another theorem that depend on the theorem you try to predict.
Yeah.
That's why there was this.
Yeah, exactly. Yeah. I know. but this was just some very fast thing how to give to losses and nearest neighbor for every each time.
I'm only doing. That's why I have preselection.
Yeah.
To cheat a bit.
Yeah. He's actually in a similar place as you are. Like he gets some huge set of previous Tableau states, and he wants to quickly pre-select only 1,000 on which he runs this compression evaluation because the compression is slow. So.
Okay. Yeah. But I still run my SML for pre-selection because it's just a pre-processing for the proof search, so it's not run during the proof search. So if it takes 2 seconds, it's not so bad.
Yeah.
Even and it's I guess it's not so much worse than the C++. It's maybe even better because I'm not printing out the file.
Yeah.
So maybe it's even better because of the overhead of printing a file.
Yeah.
Because KNN is very simple algorithm.
Yeah.
So it's just linear on just 100,000 multiplications.
Yeah.
Or a bit more.
Yeah.
Because you have many features.
Yeah. Well, it doesn't have to be simple. Like when it became unpleasantly slow for Mizar, we looked at some indexing lists. Like there are indexings for KNN, which makes it faster. But quite often they make it only approximate, so you may miss something like because the indexing needs to be sort of high dimensional indexing. So there are various methods how to do it.
There are some methods to make it. If the dimension is not too high, you can make KNN fast, but your dimension is like it's like every different term is a feature. So that's why you have embeddings to
actually doing embeddings in one of the ways.
Then nearest neighbor with some clever tricks.
Yeah.
You can be less than linear.
Yeah. Yeah,
like
but then
tree structure.
yeah,
that goes.
but then you are just interested, especially because in every formula you typically have some inequality or some bullshit like this.
Yes.
So you have to sort of consider practically every formula.
Yeah, of course. But if you have the graph already made, you have some pre-graph, like, I don't know how it works when you have low dimension canon, like one dimension canon. I can imagine that you go one way and then you go the other way, you do something like this. And then and for two dimension canon you do something like circle, like spiral. Three dimension I'm not sure anymore.
Well, it's a spiral in 3D space.
Yes. I'm not so sure if it works too
Right, so for the last talk of the day, Zarathustra was going to tell us about what's just going on my side.
So we did some experiments on watchlist guidance in Mizar, and you'll hear more about what that means soon. The watch list basically contains clauses that can be used to guide these search for a proof. These have been used in Prover 9 by Bob Neroff to help prove some substantial proofs, and they've been called hints. In this work, we usually just use clauses from previous proofs that E has done before. However, you can also think of it as choosing mathematical tricks or conjecture, lemmas, or sum goals. We are learning from previous proofs, and currently we had about a 7.2% increase in proofs proven in the Mizar mathematical library. And we have some longer ones that have only been proved using watchlist guidance. Initially for AITP 2018, we experimented with ways of including watchlist guidance in E strategies by a priority function, and how to build the watch list from previous proofs. And since then, we've continued with making the watch list guidance slightly more robust by allowing skull and symbols to be treated as the same if they have the same arity, so that you don't have Skolem naming inconsistencies. And we've tested dynamic weighting of hints on the watch lists, which can be a measure of how close one is to proof completion, and K&N recommendation of hints. Where is the AI in this? We are learning from prior proofs, and the watch list, in a sense, provides a logical interface between a human or more high-level AI methods and the ATP. So we can have higher-level AI methods that think about where the current conjecture, how the current conjecture relates to other conjectures or proofs in the same field of math or Mizar article, and provide some guidance to the ATP like that. And with dynamic weighting, we have a sort of vectorial representation of the proof state that could be fed to something like Enigma that Jan Jakubuv presented earlier as some extra features. The E, as was covered just 2 talks ago, is a saturation-based reputational theorem prover that basically repeats this loop until we get a contradiction or run out of time. In this loop, the way we are trying to help E be smarter is by selecting the clauses more intelligently and ideally with more conjecture but specific guidance. The basic watch list mechanism, if you're using the prefer watch list priority function, is that we check for each clause whether it subsumes a hint or not. So if this hint comes from a previous proof, that means some inferences following from this hint led to the empty set, so it's probably a good direction to search for refutation again. So then we boost the priority and thus the score, making E more likely to select this clause as a given clause. And we remove the hint from the watch list. So what is priority or score and weight? He chooses given clauses via a weighted round-robin selection with different priority queues is specified in the strategy containing clause evaluation functions. And Jan also covered this, so the FIFO weight function with the preferred processed priority function will be used twice as much as this other one. And this is an example of one of the actual strategies that we evolved to use. It has a bunch of clause evaluation functions and other parameters. With the dynamic watch list, we actually keep multiple watch lists, one for each proof that's loaded, so that we can keep track of which prior proofs hints come from. So that if one watch list has most of the proofs matched in the current proof search, then we know that we are likely close to the completion of a proof. So it's not necessarily guaranteed. And depending on the percent covered, there's a different priority function that gives more priority depending on how close it is to completion. So if you have a bunch of these watch lists of varying degree of completion in the same user article, this represents a sort of proof state that's we also have a version that's where clauses that are inferred inherit their priority from their parent. Because you don't just want to match a clause on the watch list and use it to generate more clauses and then completely treat them normally. It's likely you want to keep doing inference in that direction. This is where we calculate the relevance. So if C matches at least one watch list, then we take the relevance from the watch list with the most relevance, which is basically how many clauses have been matched on the watch list versus how big the watch list is. However, due to the way priority functions in E work, if you have a priority of if you have a priority of 40 and like 39.99, the 39.99 will be preferred. So then eventually we want the relevance to decay to 0. So that we will also choose as given clauses that have no relation to the watch list. Which we do if the relevance is small enough based on this multiplicative decay, and we add in a threshold parameter for the weight, for the length. So if we get clauses that are too big, we also deprioritize them a bit here. So for our experimental setup, we use almost 58,000 USAR40 conjectures with the premises pre-selected. And we previously evolved 32 strategies with decent coverage, and this is running each of them for 5 seconds each and putting the total together. In practice, we use a 3D cover of just 5 of these strategies, 2, 8, 9, 26, and 28, which cover 21,000. So we have some options for how to put the prefer watch list priority function into strategies. One option is Stefan Schulz evolved a decent strategy for using the watch list, which includes 4 clause evaluation functions, and the ones that use the watch list.
Besides, we evolved a non-watch list function and just replaced some of the preferred functions.
Okay. I didn't know. Okay.
That's why we have this meeting.
Okay, so what you did is actually much more similar to what we've done then.
Yeah.
Okay. Okay, so you evolve normal functions and put prefer watch list in. But it performs pretty well, and it's the most useful weight function is this one. So one option we have is to take the strategies like that long one I showed you before and add in conjecture relative symbol weight with prefer watch list with parameters as in this use watch list evo strategy, so that this clause evaluation function is used half of the time. Another method is to take all of the priority functions in a given strategy that we're using as a baseline and just replace them all with prefer watch list. And another option we tested is to modify E so that it uses the normal, so it uses the baseline's priority function, but if a clause subsumes a clause from a hint of the watch list, then we treat it as if we were using prefer watch list. So it's sort of like a combination of prefer watch list with the other priority functions. And there's the version where when we're doing this assumption check for the watch list, we treat Scholem symbols as the same, but in the rest of E, there's no change to that. And then there are the dynamic strategies, which the main one used is the same as this, except we use prefer watch list relevant instead of prefer watch list. And basically likewise for with the decayed inheritance of priority. So to create the watch list first, we tried just taking all the clauses from previous proofs from these baseline strategies, but at a bit over 100,000 clauses, that was way too slow. Something that works okay was to take proof clauses from the other conjectures proofs in the same Mizar article, which is between 1 and 4,000, depending on whether you have any proofs in that article. Another option is to use the most frequent clauses from other proofs, which then is more in line with the idea that the watch list could be like a bag of useful tricks or something. And we've used K and N to suggest proofs whose clauses to include. To do is to use more sophisticated machine learning or AI methods to suggest clauses or relevant proofs for a given conjecture. This is informal testing, just to see how things work, and clauses from proofs done by the same strategy were generally more helpful. Using very small watch lists, it was helpful to not remove hints once they're matched on the watch list. The default weight for a watch list was not very useful. So that indicates that the weight functions are quite useful. Including hints in the per article basis seems okay for some things. So I did some tests with just the most frequent clauses. So that's the top 10, 100, 256, and on the top we're using the top 10 clauses from the same article, in which case the top 10 actually perform slightly better. Significantly, which is interesting. But with the process clauses per second, we can notice that up to around 500, the speed was okay and then decreased. But I think we improved the speed a bit after this. This is the larger benchmark of taking the clauses from the same article. We ran each of these for 10 seconds on a random sample of 5,000 conjectures, and if a proof was done by the baseline, we did not include that proof in the watch list. Although if you do include the proof in the watch list, he usually manages to prove that.
What happens if you run 100 seconds or 200 seconds?
100 seconds? Yes, did you run them a bit longer?
No, not in this evaluation.
200 seconds, we did not do much on.
Well, then let me put it another way. How many of your proofs are coming in the last one of the 10 seconds? Are they mostly coming in the first 2 seconds?
Well, in general, the experience is that B solves half of whatever solves in the first second and half of the rest in the second second.
Yeah.
Of course, what just slows it down, but I guess that's most of the proofs are found quickly. It's like Michael told us earlier, I think, either we solve it fast or we don't solve it at all. It's a good rule of thumb.
Yeah, it's generally the same. I think, initially when doing the testing, I was doing it with 5 seconds, and we did increase it to 10, but there was not that significant an increase between 5 and 10.
Not enough to tempt you to try 20.
Try 20? I don't remember exactly what they were, but we did try some tests going for 30 seconds. It was a bit better, but not really enough to warrant being able to do 1/3 of the experiments. Well, one interesting observation you noticed is that this pref baseline, where we use this prefer watch list but do not give it a watch list, which means it basically doesn't use the priority functions, which seems to improve most of our baseline strategies. But fortunately, using the watch list in various ways improves upon the baseline strategies more. So the success of using the basically constant priority function may indicate why combining the prefer watch list with the other priority functions did not perform as well as I might have expected. The use watch list Evo performs pretty well, but it's basically one strategy, whereas this is an ensemble. And the matching treating school and symbols by RT alone does seem to help as well. So this is the dynamic version just on the per article basis. This is our greedy 5 top cover of all of the conjectures, which is significantly better than just the baseline. We also ran auto schedule for 50 seconds to get a rough comparison. Next, we wanted to do some tests of using K&N to suggest proofs for the given conjectures. So I think we did this with using simple and term-based features for the conjectures and labeling them with the different clauses that were used in them. Let's see. So the best of this one uses the 32 most similar proofs. So it increased from 1500 to 1546. So using the K&N suggested proofs is also quite helpful. This time, after this, we ran this top 5 greedy cover on the full data set of around 58,000 conjectures to get more data. So then we have a data collection of E outputs whenever a clause is matched to the watch list and tells us which proofs were matched more and which less. So then we looked at in the final proof which clauses in the final proof came from a certain in the proof of a given conjecture, we looked at which clauses came from matching the watch list clause or not. And in the next round, we also add to the K&N training examples containing the names of proofs that contributed to a given given conjecture's proof. And this again increased the performance of some of them by around 20 proofs. However, in total, only 9. These are the results of the full runs of the covers for the first and second round. And then we used the same suggested watch list as for the second round of the dynamic K&N test to test the dynamic inheritance watch list. And it actually did significantly worse than the other watch list based methods. However, there is something interesting about it. This is a table of conjectures proven by a certain method that were not proven by the baseline method. So it turns out that with the dynamic inheritance watch list methods, E actually proves significantly more conjectures that were not proven by the baseline strategies than the other watch list strategies did. However, it seems that more tuning might be needed to prevent it from distracting E as well. taking this is a top 5 reading cover from all of the experiment runs we did on the 5000 S set. So this 2007 is about a 2% improvement over the initial benchmark we did with the per article based watch list and the baseline combined. And we ran this reading cover on the full data set, so then this is the dynamic with inheritance, dynamic and dynamic with inheritance, which then gets us to around 23,000 injections proven, which leads to the 7% improvement over the baseline. Now we have an example of a proof that we found thanks to the watch list, which Jakubuv will have the pleasure of presenting.
Okay. Because we have a bit more time today, I decided to try to say something about the bigger motivation for this first. So the reason why we got into watch lists is that it really works very nicely for Goertzel. Like he has these algebraic problems where, with my opinion, they are solving open conjectures, and by the watch list guidance mechanism, by solving problems that are related and putting the clauses from the proofs on the watch list, they really get proofs which are beyond what we have seen in this sort of hammer territory. Like what we get in the hammer territory are proofs of lengths 100. What Bob gets on his algebraic domain are proofs of lengths 100,000. So it's sort of unusual to get such long proofs in the saturation style of automated theories. So the first step here was to realize that Bob is in a very unified domain, and what mostly helps and works for him is to put all the proofs he has so far, like he also sometimes does some manual solution, but in principle what he does is put all the proofs he has so far on the watch list and hope that it will work. If you do this on something like the Nizar library, when you have very, very different parts of mathematics covered, it will not work. So you need to do some pre-selection of the related proofs, and that's why we are using K-means library, for example, to select just the 32, 100, 1000 most related proofs, which will guide the proof. The second motivation, which we sort of realized slightly later, but it actually might be the most important thing on this work, is that when you load into your proof state something like, let's say, 100 or 500 or 1000 related proofs, and you can use this as something with what Michael wanted in his previous talk, which is this sort of abstract, vectorial, reasonable semantics characterization of your proof state and how it evolves. So far in situation style theorem proving, what is considered to be the proof state are basically two piles of clauses, the pile of process clauses and the pile of unprocessed clauses. And now, like Michael was saying, you somehow have to define features of these two piles of clauses, and that's not trivial. So in like total abstraction, what we would like to have is some sort of abstract vectorial representation, some sort of evolving hidden state, which will be helping the guidance to guide the selection of the next given clauses. And so far, like what we have done with Jan on Enigma and what Sarah and Christian and Diffrit have done and Cesar have done on like using neural network for guiding e-prover is in both cases extremely limited, because it basically only uses the conjecture, which is stated in the very beginning to guide the selection of the clauses during the process. But it's like basically ignoring whatever has happened during the proof search. Like it's like saying, I have this ultimate goal up here, and I will totally ignore what I have proved or inferred so far. I will just like try to choose from what I have inferred so far, something which like gives me the best score with respect to the conjecture. So if you compare this to what Tibble was showing, what Cesare was showing on Linko, there the situation is much better because we have sort of an evolving characterization of the proof state, both in Tableau and in technical style theorem proofs. So in some sense, this is the first attempt to have some reasonable evolving characterization of the proof state in saturation style theorem proofs. And in this particular case, it's the vector of, let's say, 100 floats, which tell us you are this close to proof number 1, you are that close to proof number 2, etc., etc. So this is basically a float vector, which can be used as a sort of evolving characterization. So that's my motivation, shameless plug. And now I'm supposed to explain to you the particular proofs that we have found, like the examples. So the first one, where was it? Here. This is a reasonably hard theorem about Boolean lattices, basically stating De Morgan laws for the Boolean lattice. And so this theorem we could prove without it, but this sort of more given clause loops. And what happened that when we put onto the watch list sort of related theorem, but not entirely related theorem in the sense that it uses, it's a weaker theorem or a theorem done in a weaker setting for hiding lattices instead of for Boolean lattices. But the proof of that particular theorem, when you put it on the watch list, seem to have directed the proof of the top theorem very significantly. So we had something like 80% of that proof of the clauses, of the proof clauses of the bottom proof used also in the proof of the guys. So this is some statistics about it. So we loaded 32 related proofs, which gave us something like 2,000 clauses on the watch list, which is still sort of manageable because the subsumption checking is reasonably fast. So basically, when we do every inference, we need to check subsumption against these 2,000 clauses on the watch list. Then the final proof, the whole proof search is something like 5,000 given clause loops. Of those, 436 is the actual ATB proof. So this is actually a pretty unusual length for a hammer style proof done by an ATB. Like, as I said, typically we get proofs of length like 20 up to 100. So this is already quite good. And something like 120 of the clauses that have been matched during this watchlist subsumption actually ended up being part of the final. So we had quite a good success rate. Like what matches the watch list is actually reasonably healthy in the final proof. And in this case, we could find the proof also without the watch list, but there's something like 25% more given customers. This is to give you an idea how the sort of abstract vectorial hidden state of this sort of saturation style prover looks when we use this sort of loaded previous proofs. So this is the final state before we have derived contradiction. So we have these 32 proofs loaded, and just before we derived contradiction, we had like various coverage of these different proofs in the internal state of the prover basically. So the one which is bold is this bottom proof of this sort of Heiting lattice theorem, which in the end has been covered like from 80%, like 60 clauses out of 7 have been covered. So this is just one more example which we couldn't prove without the watchlist guidance. So it's again about Boolean lattices, and then there is some sort of symmetric difference theorem helped by 3 other theorems about Boolean lattices. And again, you can see that none of them is exactly what we are doing, but in the proofs of these theorems, the clauses that were contributing were also useful for proving this theorem. So as I said, like we could prove this in 1.2 seconds, but we couldn't prove it with any other strategy in 10 seconds. And the proof again is unusually long, so it's like 633 inferences long. And a very high number of the clauses actually matched the watch list. So not all of them ended up being part of the proof, but you can consider this sort of getting to the world of Bob Verov and the sort of algebraic equational technology that he developed. Like for him, it also wasn't immediately proofs which are 100,000 inferences long. So he was starting with proofs which are like several hundred and several thousand proofs long. So I think hopefully it looks like we might be eventually getting there to really get proofs of this technology. And that's my input.
Okay, so for very brief comments on other things that we can try. One is to try and calculate the distance, how close. So when we match many clauses on a proof in the watch list, it might be good to have an estimate of how close that proof is, the clauses in that proof are to a contradiction in the conclusion of that proof, so that we would value it more if we were close to the end rather than close to the start of some proof in the watch list. Something else is that this proof state will change over time as he looks for a refutation. So it would be good to every n given clauses or n matches of the watch list reevaluate developments. As we did with the scroll and symbol matching, it might be good to look for other ways to do approximate matching. It might be nice to try and calculate the distance to some watch list clause, so that you have more. That's another way of getting approximate matching. At least it's close enough. This proof state vector could also be passed to other methods that are faster inside E to help them with their given clause selection, such as Enigma. That's it.
Questions?
So can you also, from unsuccessful proofs, can you export some proof state vectors? So let's say you try to prove something and then I would like to see, so I mean I want to get some intermediate representation of where is my proof.
So basically every proof round that we have is in the debug mode is printing after every successful watchlist subsumption is printing the proof state vector basically, which is expressed as this vector of the current proofs.
Every time the proof state changes, it gets printed out if you are the right output mode.
So we actually got asked by some reviewers like if we can make all the experiments available, and the issue with that is that we have like over 100 gigabytes of compressed data because each of these proof runs, like we are learning from them in the next iteration. So we need to run them in this debug mode, and I don't know how big are the files. Like it's
1024.
Yeah. If you
one was
yeah
75 gigabytes.
yeah.
So are the intermediate states important? So let's say if I would just like to have the last proof state or something.
Yeah, let's see.
Okay.
Okay. I'm not sure I can clarify how the projects get into the watchlist. How much? Maybe I didn't get it.
The easiest way to put them in the watch list is like if you're proving. The easiest way was the per article way, in which if you're trying to prove this Wavell conjecture in this Wavell article, you look for the other proofs that we already have from E in the Wavell article, and we take every single clause from those proofs and add them to it. On our data set, however, ideally it would be interesting to try and combine watch list hint selection with premise selection, as there's probably synergy there to be tapped.
So there are these two modes, like the original Bob-Berth mode, when you take as many proofs as you have, or some proofs selected by premise selection, and you all dump it into one watch list. That's the original method. And then there is the dynamic watchlist guidance, which is sort of the new thing here, where each of these proofs is treated separately. So each of them gets their own watch list. So we have, 32 up to, let's say, 1,000 watch lists loaded in eProver. And that gives us the sort of proof search vector for.
Although in principle you could use some other watch list heuristic besides proofs, if you have a good idea for that.
Probably a more general question, but related to this. So I mean, if you're using the proofs to learn, what's the status of simplifying proofs? So I mean, if the proof has a lot of garbage, then it's not useful. So I mean, that's kind of obvious. So what's the current status on that?
It's a black magic done by Stefan.
Okay.
So indeed, both Bob and Stefan have to somehow take care of the simplifications and the rewritings when they do things with the watch list. So the
what this is kept normalized with respect to the current process system, just like the process one.
So during the proof search, you are normalizing the watchlist clauses with the rewrite rules that you have inferred basically.
But I mean, after I have found the proof, I still can simplify it, right? I mean, it's always gonna be some redundancy.
Oh yeah, you can of course every proof can be somehow post-processed, minimized, etc., etc. So in this work, I'm not sure we did it. Probably not. I don't think we have done some exhaustive minimization.
I think we're talking about simplification of clauses using contracting inferences, basically of rewriting and subsumption resolution, not about the structure of the whole proof.
Yeah.
It might be possible. It might be that we don't necessarily want to take every single step from the relevant proof either, which is a reason to try and do a more advanced.
Yeah,
Yeah,
exactly. Yeah.
Which clauses and proofs to include on the watch list.
So currently we really use this very fast subsumption thing which every theorem proving person has implemented and indexed, but we could obviously do some sort of embedding thing, right? Like we could embed the clauses from the proofs and do some similarity check rather than the subsumption check from them.
Okay, so what are the motivations for the work? Where these large groups coming from Goertzel and so on? Is now the replacement for Kubernetes method of this work, or is it still to be compared?
So in Kubernetes 9, there are some more relaxed matching conditions. They allow for patterns of clauses that can be matched, and have a quite complex language to simplify that. So this is still a little bit beyond what we are doing. I'm not sure how big the difference in practice is.
Yeah.
Bob has the opposite way of working than I have. I look at a bunch of problems in how the proof performs, and I don't look into the proofs at all. I have machines doing that. And Bob looks at each proof very carefully with a magnifying glass, each clause, and tries to make it nicer. So it's very different approaches to the same area.
So Bob comes to Prague in 2 weeks, and he's willing to experiment with eProver.
Okay. No one else? Okay, well, thanks very much again. I think that's it. The programme says discussion on free time, and there's no discussion time. Everyone's free.
Yeah. Oh, I should make some. I think I almost forgot again. So the people at the conference center are asking you 2 things. If you want a lunch package for tomorrow, today during the dinner, put the information to some sort of they have there in the corner. You will see it. And the second information is put your arrival info, basically what you put into the Google Doc, on some paper at the reception, and then they will organize the taxis based on the info that they have in the paper to tomorrow. So that I'm out of the loop, and they will do the work for us. So basically, each of you, if you want some taxi, then put your info there.
How long does it take to walk?
How fast are you?
Because I have a backpack and a suitcase, so slow.
Well,
I think
2
the
hours.
fastest way is over that way where that direct way that is currently blocked for cars. There is however snow, so you will have to carry your suitcase at some places, not at many, but still at some.
2 hours downhill.
Yeah, 2 hours. That's what I heard.
That's all from me. If anybody has any discussion topics, then like whatever, or we can also slowly progress towards the dinner.
Google Maps says 2 hours.